Okay, so this slide here sort of summarizes everything we've said up to now and applies it. We have our injector conditions, the nozzle design, the radius of curvature of the inlet of the nozzle, the length of the passage. These are used to determine essentially the velocity of the jet at the exit of the nozzle and also the diameter of the jet because of the flow contraction effects. So how do you go from that to a Lagrangian drop model? Well, we have introduced what we call the blob injection model. So we inject parcels of drops that have diameters equal to that effective nozzle diameter. And we allow those droplets or parcels or chunks of liquid, or blobs, whatever you want to call them, to break up using the Kelvin-Helmholtz and Rayleigh-Taylor models. As I mentioned before, the Kelvin-Helmholtz models really apply mostly in the region of the jet near the nozzle exit. And that forms, as we mentioned, the primary breakup. And then we have the secondary breakup of the formed droplets. So this region where the Kelvin-Helmholtz is mostly influential is in what's called the breakup length region. And we showed how you can calculate that using this wave stability theory. Once the droplets are formed, they then undergo Rayleigh-Taylor breakup due to this great, in this case, deceleration that they experience as they're injected into the high gas density environment. In addition to the breakup, they undergo collisions and coalescences and so on. The droplets themselves then interact with the surrounding gas through droplet drag, which we're going to talk about. Eventually, they may impinge on surfaces, so we have to worry about spray wall impingement. And during this whole process, they undergo vaporization. And typically, real fuels are multi-component, so we have to take into account that aspect of things as well. So let's talk first about droplet drag. Essentially, here we have the droplet acceleration equals to this acceleration function f here that we described earlier that is needed when we go to the source terms in the gas equation. So how do we calculate f? If you look in the literature, lighter work has been done on drag around objects, and in particular for spherical particles. This first term here is so-called Stokes viscous drag, involves the viscosity of the gas phase. Here we have the added mass term. Generally, this is very small because the gas density is much smaller than the liquid density. And then we have this last term, the so-called Bassett history term, which essentially is most important during the startup of the, when a droplet is suddenly exposed to a velocity of the gas. Generally, this term is also neglected. And in fact, what is typically done is the equation is written in this form, where we have the liquid drop density, the volume of the drop, so this is the mass of the drop, times the acceleration, equals a force. The force is the dynamic pressure in the gas density times the relative velocity between the drop and the gas, u squared here, times the frontal area of the drop. So if it's flattened, we'll see that that's affected, as is the drop drag coefficient. So we need a drag coefficient. And literature on drag around spheres shows that there is a region where Stokes drag is applied at low Reynolds number, that's 24 over Reynolds number. And then for high enough droplet Reynolds numbers, the drag coefficient is taken to be a constant. So that's the way this is implemented in, say, the original Kiva code. Yeah?
This will be applied to an individual droplet or the parcel?
So individual droplets inside the parcel, so they all get the same treatment inside that parcel. Okay, so how do you take into account other effects such as the distortion of the droplet? Again, Taylor in the 1940s proposed this Taylor analogy model, where essentially he calculates the distortion of the droplet, and this parameter y here is a non-dimensional distortion, non-dimensionalized by the radius of the drop. Here is his governing equation. It's a second-order ordinary differential equation. The inertia term on the left-hand side. Here's the viscous damping term. You see the liquid viscosity, the liquid density, the radius of the drop. And then there's a term due to surface tension, which is like a spring mass system. So this would be the spring in the spring mass system, surface tension, liquid density. And then finally the forcing function, which is that dynamic pressure term, the relative velocity between the drop and the gas. And here we have the gas density and the liquid density. So if you solve this equation as a function of time, you can calculate essentially how distorted the drop becomes. And you can store that as part of the characteristics that describe this particular assemblage of drops in your parcel. Turns out that if you solve this equation, one limiting solution is when the droplet becomes flattened. In other words, y becomes equal to the radius of the drop. And then it looks like a disk. If you look in the literature, the drag coefficient for a disk is 1 plus 2.632 times the drag coefficient of a sphere. So basically, the approach we've taken, and it's described in this paper here, is to essentially use the droplet distortion to get a better estimate of what the droplet drag coefficient would be for realistic droplets. Okay, so the other aspect is the relative velocity between the drop and the gas, and this kind of goes to your question earlier, is that droplet is going to be influenced by the turbulence in the eddy that the droplet is located in. So actually, if you this picture over here just shows conceptually the types of interactions that you might expect between a droplet and a turbulent eddy. If you imagine vortices in a flow, those vortices have a certain characteristic time, and droplets have a certain characteristic time to adjust to the flow in that vortex. The measure of that is this Struhol number, I guess that's what it's called, where essentially if the droplet is very small, I'm sorry, wait a minute. I wonder if I have this written right. Oh, yeah. If the droplet is very large, it behaves like a cannonball and just moves the way through these turbulent eddies. It's unaffected by them. On the other hand, if the droplet is very small, it will become influenced by those turbulence eddies, and it gets essentially trapped in them. And then you're going to have a situation in between. So these parameters here essentially account for the interaction between the droplet and the surrounding flow. Okay, so how do we characterize that turbulent flow? We have a mean flow, which comes from our Rand's models. And then we have fluctuating velocity. How do we pick this? Well, we know that the turbulent intensity is related to the kinetic energy of the turbulence. And Gosman and his group devised this strategy. They said, well, let's consider this to be a random process. We'll assume we have some kind of a Gaussian distribution of turbulent velocities. The width of the distribution will be determined by the turbulence kinetic energy. And we'll pick at random this left-hand side, again, a number going from 0 to 1. And then, knowing the turbulence kinetic energy in that particular computational cell, we can calculate a U prime. So that gives us essentially a measure of what type of turbulence to expect in that computational cell. So then the next step is to say, well, we're going to define a droplet eddy interaction time, which will be the minimum of two potential times. One is the eddy lifetime. The eddy lifetime is determined knowing the length scale of the eddy, which comes from the K epsilon model, and the turbulence kinetic energy. So basically, a drop can only remain in an eddy for as long as that eddy exists. So that's the T sub E here. The other is in this case where we have a cannonball type of interaction. As long as the droplet remains in that eddy, which now is going to be determined by the size of the eddy and the relative velocity between the drop and the gas. So we take the minimum of these two times. Once this time has been reached, we then go back and sample for a new U prime, because now the droplet is in a new eddy. and in this way account for the effect of turbulence. This is a very simple but effective treatment, because basically what that allows you to predict is the dispersion of a spray. You have these droplets, they're getting nudged by the turbulence. They're getting nudged in the correct amount, because you're assuming that you have this Gaussian distribution of turbulent velocities, and that allows the spray to spread. Yeah.
So why is there a need for this sort of model if there's a link between, say, the fluid velocity and then the particles, the droplets are being moved by the turbulent flow? Why is that not sufficient?
Okay, so in the Rance model, we only have some sort of an average representation of the flow field. This allows you to add that element of a stochastic process.
So in something like an LES, you probably wouldn't need this?
Exactly.
Okay.
Exactly, yeah. Okay, so that's droplet drag. If we talk now about spray wall impingement, again, this is an area that a lot of work has been done, especially by the nukies, because they're interested in cooling in nuclear reactors and so on. Anyway, if you go back and look at the classic literature, one of the classic papers is shown here. What they plotted, Wachters and Westerling, is the Weber number, this is based on liquid properties again, of the outgoing droplet versus the Weber number of the incoming droplet. Okay, so what does this mean? Weber number is defined as the normal component of velocity squared. So if I take a ball and I calculate its Weber number as it approaches a surface, I would use the normal component of velocity. So it's like having a head-on collision, if you like. And what this says is that at low values of incoming droplet Weber number, the droplet bounces off the wall with Weber number out equal to Weber number in, which is this straight line here. But as I increase the Weber number of the incoming droplet, some energy is dissipated during the interaction with the wall. The droplet flattens and basically loses some of its kinetic energy. And so I don't follow the elastic bounce curve anymore. And in fact, I reach a maximum, and then eventually the outgoing droplet doesn't even leave the wall. The liquid spreads across the surface of the wall. So the outgoing Weber number goes to 0. So beyond a Weber number of about 40, the liquid spreads across the surface. So you can see that as kind of a picture here. For Weber numbers less than 40, you have a droplet approaching a wall, bouncing or reflecting off the wall. It could then undergo breakup and so on. For Weber numbers greater than 40, the droplet will hit the wall and then slide along the wall. So we developed a theory back in the late 80s to describe the various regimes. This is what your guys who use spray painting equipment rely on, is that if you have low enough incoming droplet Weber numbers, you can cause the droplets to actually stick on the surface. So that's the stick regime. Then the spray painter really doesn't want this. This is where the droplet bounces off the wall. And then finally, this is the jet regime. So droplet approaches the wall and then slides along the wall. Now, if this is a train of droplets that's hitting the wall, like, I don't know if you've ever watched when you use your garden hose on your driveway, you'll notice some of the fluid goes that way, but some of the fluid actually goes in the opposite direction. So for a train of droplets, to try to account for that, we developed a theory that basically considers the mass and momentum of the stream of droplets entering or being directed at the wall, and then a conservation with looking at the mass and momentum in the azimuthal direction to determine how much of the liquid actually flows opposite to the direction of the incoming jet. And we came up with this expression here. Phi here is the angle. P is a random number again in the spirit of a stochastic model going between 0 and 1. So when a parcel of drops hits the surface, we pick a random number between 0 and 1. Of course, its Weber number has to be greater than 40 before we do that. And then determine essentially the trajectory of those drops that have hit the surface. So that model is implemented in many codes now that deal with spray wall impingement. And this just shows some validation data that we did for a very simple experiment, but effective, where we have a nozzle that's injecting a spray down onto a target, which in this case was just a flat pedestal arrangement. And then we measure the penetration of this deflected jet as a function of time, and we get plots like this. This is the penetration of the jet from the axis of symmetry here as a function of time. And you see the lines are predictions, the symbols are measurements for two different cases. And this actually works quite well. Yeah?
For the jet regime, how is the treatment when the volumetric loading is over 90%? Is there a different treatment for cells in the model?
Yeah, so that's a good question. Nobody really has pursued that because in most applications, the cell sizes are still big enough that the void fraction there's a lot of gas in the cell. But you can imagine if you try to refine the cells near the wall, eventually you'll have a problem. Fortunately, when that happens, codes do not crash. But it's something you have to be aware of. Yeah. The equations basically are no longer valid. Yeah.
With this slide here, when the droplets are bouncing backwards
Yep.
to the second figure, is that because they're interacting with other droplets or droplets on the surface?
No, this is just what happens if you have a continuous stream of liquid. If, like I said on your driveway, if you spray a liquid jet. So now imagine that that jet is actually made up of a group of droplets. It will behave like a continuous stream. And in fact, they are interacting with each other in the continuous stream. Yeah. So it's just a simplification to account for, to kind of combine the idea of treating a liquid spray or liquid jet as blobs of liquid. Okay, so the other thing that happens when a spray impinges on a surface is that the droplets become destabilized, if you like. Remember I mentioned that there were some constants in the breakup models that essentially associate a breakup time with some initial condition, some initial disturbance. In the case of the nozzle injection, it was cavitation processes in the nozzle. Here we have a huge disturbance being imposed on these droplets as they hit a surface and so on. And we found that we need to change the value of that constant that determines the breakup time when a droplet hits a surface. And that's how we're able to match data like you see here. Okay. So next thing we've discussed a little bit before about multi-component fuels. So droplet vaporization. A lot of work in the literature, textbooks written that you can refer to for droplet vaporization. A lot of processes that need to be considered. Starting from the surface here, we can have equilibrium or non-equilibrium transport from the liquid phase to the gas phase. We have mass transfer. We could have condensation processes. The liquid can actually be, some of the inert gases in the liquid can be absorbed into the droplet, nitrogen solubility, for instance. We have heat transfer to the droplets through conduction, convection, and radiation. There's relative motion between the drops and the surrounding gas. And then we have flow profiles within the droplet. We can have recirculation and eddies set up inside the droplet. So very complex processes and very difficult to include in a CFD calculation where you have thousands of these droplets. So we have to do some subgrid scale modeling once again. Just for reference here, this just shows distance away from the surface of the drop, the mass fraction, say, of the fuel, and a temperature profile associated with high temperature ambient and the surface of the drop. Okay, so all of that has to be somehow included in a model. For single component, low pressure environment, we are familiar with the so-called D-squared law, was mentioned by somebody, which describes the droplet vaporization process very well. And this is actually built into many codes, including in the Kiva code, where that parameter R, the rate of radius change with time, is determined knowing a diffusion coefficient, this parameter B, the mass transfer number, which measures the difference between the mass fraction of a component at the surface of the droplet and the mass fraction far away from the droplet. So that's B, the transfer number, sometimes called Spaulding's transfer number. And then we have the Sherwood number, which has this additional correction to account for convective effects. And then the density of the droplet and the radius of the drop. So if all this stuff over here is a constant, and we can take this r to this side here, we get r dr dt is a constant, then we get the d squared law, right? That's r squared is linearly changing with time. To determine the fuel mass fraction of the drop surface, we need to know the vapor pressure, which is a function of the droplet temperature. And in most codes, it's assumed that the droplet temperature is uniform inside the droplet and all the way to the surface. So if we know that number, we can calculate the vapor pressure that gives us the mass fraction at the surface, and hence we can calculate the vaporization rate. How do we get the drop temperature? Well, we have to look at an energy balance. So here we have the mass of liquid in the droplet, density times volume. Here's the specific heat, rate of change of droplet temperature. So this is our unsteady term. And that's then balanced by the latent heat term times the surface area and the rate of change of droplet radius. So this is latent heat effect. And then this is the heat contribution from, say, the gas phase to the droplet. And that would be calculated with some sort of correlation involving the Nusselt number, for instance. Just like we had for mass transfer, now we have a correlation for heat transfer. And the temperature difference between the gas and the drop. So these, again, are simple models that are sort of the base models that are used in codes like Kiva. However, if you look at droplet vaporization, we're actually interested in more than that simple situation. We are, of course, interested in normal evaporation with heating and cooling. Also, boiling vaporization, where the surface temperature is the same as the boiling temperature. And then flash boiling, where we could actually have a situation where the droplet temperature and or the environment temperature is actually greater than the boiling temperature. And so essentially this droplet should, if we only accounted for just the one temperature here, would disappear instantly. So to prevent that, we have developed a model, and it's described in some of these papers, where we account for the boundary layer and a boundary layer at the surface of the droplet. So we can actually have two temperatures. One is kind of the droplet internal temperature, and the other is the droplet surface temperature. And then we can account for heat that is transferred from the environment to the drop, or heat that's transferred from the internals of the drop to the surface. And this allows you to then deal with these various regimes of vaporization. So a busy slide here, but basically, if we just look at the surface boundary condition, we have the mass transfer rate, or the droplet vaporization rate, m dot here, times the latent heat, which depends on the surface temperature of the droplet. And that's going to be balanced by the heat coming from the internals of the drop due to the drop temperature being higher than the surface temperature, and from heat transferred from the exterior to the surface of the drop. So if you look at this equation and look first at the first term on the left-hand side, this is the driving force is the difference between the drop temperature and the surface temperature. We need a heat transfer coefficient, h here. H is determined knowing the conductivity of the droplet material and a boundary layer thickness, this thickness here, which determines essentially the gradient of temperature at the vicinity of the surface. How do we get that boundary layer thickness? A lot of people have done work, for example, Bill Soriano's group, that have shown that essentially this boundary layer thickness grows as the square root of time. It's a diffusion problem with some sort of effective diffusivity. And that effective diffusivity depends on the Reynolds number of the drop and so on. So that's included in this analysis. So basically, as time goes by, the boundary layer thickness grows here, and that changes the effective heat transfer coefficient for the interior heat transfer component. For the heat transfer from the gas to the droplet, we have the difference between the temperature far away from the drop, T infinity, and the surface temperature as being the driving force. This term in this ellipse here is the effective heat transfer coefficient, which is derived in this paper here. It depends basically on the mass transfer rate, Nusselt number, thermal conductivity, Sherwood number, and the difference between the fuel concentration far away from the drop and the fuel concentration at the drop surface. And other things, drop size and specific heat and so on. So the mass balance provides this result, which we saw before. It looks like the Froesling correlation. So that's basically plugged in here to get the mass transfer rate. So in the case where we have flash boiling, the surface temperature and the drop temperature are, of course, different, but the surface temperature is now given by the boiling temperature of the fluid. We get this from the Clausius-Clapeyron equation, and now we replace Ts here with T boiling. And the other thing we change is that the surface mass fraction is now equal to 1. Yeah?
How does that even occur that you end up the droplet becoming hotter than the boiling temperature? Is it because it's moving from like an area where it can't evaporate to one where it can?
That would be one explanation, yeah. Yeah. Or, for instance, it's very well known as a phenomenon that occurs when you inject a liquid that might be in the liquid phase at one pressure into an environment where the pressure is lower, and it would flash to vapor. So the other thing that you'll notice here, this circle is an augmentation to the effective heat transfer coefficient for the heat transfer process inside the drop. And this is due to nucleation phenomena that can occur when you have flash boiling. So basically, you're stirring up what's going on inside the droplet because of bubbles. We spoke a little bit about that earlier. Here are some correlations that are published in the literature that essentially depend on the amount of superheat that the droplet experiences and essentially augments that this effective heat transfer coefficient. Okay, so that's kind of a state-of-the-art vaporization model. Now, each component of the fuel in the droplet might have a different vaporization rate. So now we have to worry about multi-component fuels. And if we look at this picture here, this just shows gasoline. These are sort of representation of a typical gasoline. It's made up of aromatics, they're shown in purple here, isoparaffins, normal paraffins, naphthenes, olefins. So there's a wide variety of components, in fact, thousands of components in practical fuels. And in fact, here this list shows for 2 different types of diesels, how much is aromatic, how much of these are naphthenes, paraffins, olefins, and so on. And this has a big effect on how that fuel will perform in an engine. You'll notice that there's a wide range of carbon numbers here, let's say representing the aromatics. And so to represent this type of distribution of species in a realistic fuel requires that you consider, as I said, many components. And that's what's embodied in the so-called discrete multi-component model that I'll be telling you about in a minute. There are other approaches. For example, the continuous thermodynamics model or continuous multi-component models described in some of these papers, where you assume that you can represent the fuel composition by a distribution function that's a function of, say, molecular weight. So this parameter I here, it would have some sort of a distribution function as a function of molecular weight, and you'd use that to represent the fact that this fuel consists of many individual components. The simplest approach is what's, the traditional approach is just to say, well, I'm going to just represent the fuel with just one component. Let's call it tetradecane, and we'll say that that represents diesel. Of course, that's not a very accurate way of representing these real fuel effects. So those are 3 different types of models. The one that we're using mostly these days is the discrete multi-component model. Yep.
I guess this might be a bit of a tangent, but related to the last slide. Traditionally, or at least up until recently, we would represent gasoline with either N-heptane or isooctane. But according to that graph, aromatics are bigger than either of those. So why did it take so long to put toluene? It just didn't have a model for it until recently.
Well, that's probably one reason. Also, there are different kinds of gasolines. So I'll show you some representations, surrogate representations in a while. There was another question. Yeah.
Yeah, so you said the single component approximation doesn't do a good job of at least representing the distribution of molecular weights. But what about other components that we'd be more interested in, such as ignition delay or
Same thing. Yeah. So if you have a blend of fuels and toluene is relatively non-reactive compared to, say, a straight chain alkane, if you only assume you have the straight chain alkane, you're not going to get the right ignition delay. So yeah, it's all part of the problem. Yep. Previous one?
Here we're taking into account the energy balance between the continuum and the discrete droplet. What is it done when they hit the wall? How is it different?
Sure. Yeah, so if you use this blob idea, where droplets basically represent the liquid, whether it's a film or a jet or a spray, then you can use the same models. But in actuality, some codes, and we've had students in the past that have looked at this, they write down the same type of energy balances for a liquid film and calculate the film vaporization. It turns out that the results aren't that different, but one can certainly do that. Oops. Okay. So just to summarize then, we have the continuous multi-component model where essentially we assume a distribution function, typically a gamma function or something like that, that has parameters that are different depending on the fuel that you use. So these models were popularized probably 10 years ago. But now computers are bigger, we can actually do more, and we can represent the fuel with a discrete multi-component model. So now we can have basically on this histogram represent the distribution with a population of discrete components instead of having to approximate the whole distribution. By the way, one of the reasons we want to get away from approximating the distribution function is that you can have multi-valued distribution functions or multi-peaked functions depending on what happens when different droplets collide and coalesce and so on. It becomes very complex. So here, if we keep track of the individual components, it's a lot easier to formulate the problem. So now we solve vapor phase transport equations for each of the species that are represented inside the droplet. Essentially, we have discrete phases of the fuel and discrete phases of the vapor that we have to track. So, for example, here is, we actually did some experiments with these fuels, two different diesel fuels, a narrow cut and a Euro diesel fuel. If one were to plot these surrogate components here are shown by the histograms. If one were to plot the continuous distribution that represents that, one would have these red lines here. But in reality, what we're going to do instead is to track these individual surrogate species. There's a relatively simple model here. We have only 4 species. They're all normal alkanes to represent diesel A. And for diesel B, we actually have an isoalkane as well. And that's this guy here. So here we have 6 components to represent that fuel. So this just to show an example from some years ago. We then did a simulation with the spray models that I've been talking about, integrated with the vaporization model. And what we're plotting here is essentially the molecular weight of the fuel. The injected molecular weight is 200. All right, so that's kind of in the upper greens here. And what you're seeing in the engine is the spray droplets. There's actually some impingement of droplets on a surface here. And the colors show the distribution of molecular weight. If I pick a point in the combustion chamber, this is an early injection case, so we had a lot of time for vaporization. I'm looking here around the time of ignition, 14 degrees before top dead center. I look at this location, I see I have quite a different representation of these fuel components than if I look at this location where I had quite a bit of impingement, and I see a different distribution. That shows up a little bit more obviously when I look at this here, which was a gasoline calculation. So here we have a spray of droplets evaporating. I'm showing the fuel mass, I guess, is that? Yeah, there must be fuel mass fraction over here, total fuel mass fraction. If I look at this injector, I see all of the light ends, in this case isopentane and so on, all of the light ends are heavily populated in this part of the spray, whereas near the tip of the spray, the heavy components that haven't vaporized yet appear to be more unpopulous. So basically, if you're looking at a combustion situation where ignition delay depends on the type of fuel that you are looking at, you might expect that the ignition is going to take place at different locations depending on how much of the more reactive fuel resides at that location. So very important to take into account this type of differential vaporization process. Yeah.
How does the least-square law for the multi-component droplet come?
Okay, so we're not really using the least-squared law. We're using the equations that I showed you for the multi-component. And essentially, as I'm going to show you in a minute, we use a modification of Rolf's law, which essentially says that the concentration of vapor in of fuel in the vapor phase is related to the concentration in the liquid phase through the vapor pressure. And that's done for each component. So basically, we can actually have some components vaporizing and others condensing on the same drop, depending on the vapor pressure ratios and so on. Okay, so this brings me to the other part of these vaporization models that's pretty important. And that has to do with the fact that most fuels are non-ideal. Right? So we have a situation where the molecules can actually interact with each other, and this affects the vaporization process. So the use of Rolf's law, which essentially says that, as I just said, the mole fraction in the vapor phase, mole fraction of the component in the gas phase, is related to the mole fraction in the liquid phase by the ratio of the vapor pressure to the total pressure. That, in Rolf's law, is inaccurate for real fuels because one really needs to account for interactions, which appears through this so-called activity coefficient. There are many ways of calculating this, but the UNIFAC method is developed at NIST. It's a very popular way of handling this, and it accounts for interaction between the species. So, for example, in the UNIFAC method, you would break up your fuel molecule, in this case, say, for ethanol, into these functional groups. Polythene here, OH, CH3. And it has basically tables in the code that will tell you how these functional groups will interact with functional groups from the other species in the mixture. So if we mix ethanol with gasoline, it will take that into account. The activity coefficient consists of basically factors that take into account difference in shapes and sizes of the molecules, and then interactions or energy interactions between these functional groups. So, in the vaporization model, then, what we do is we, instead of treating each component individually, there is an interaction through these activity coefficients. So, if you look at a surrogate mixture here for ethanol and gasoline, that's published in this paper here by one of my students. We have gasoline represented as cyclopentane, toluene, methylbenzene, xylenes, and so on. And little pictures of the molecules. So this is kind of a 10 components gasoline. If you look at the functional groups that appear in the UNIFAC model, they are sort of listed here. And then you would apply that as part of your calculation. This this has actually a significant effect. This plot here shows E10, that's 10% ethanol gasoline, with and without the unifact model, for a sample problem, showing the droplet radius as a function of time. And you see, what seems like a relatively small effect here. But actually, if you look at the thermodynamics of what's happening, as shown on this plot here, which is the phase diagram, this shows essentially the boiling temperature of the gasoline ethanol mixture as a function of the amount of ethanol. So if we have no ethanol, the light ends on the gasoline start to come off around 60 centigrade with that surrogate list that I showed you. And if I don't use the interaction or count for the interaction, I get this linear increase in boiling temperature as I go up, as I increase the amount of ethanol whose boiling temperature is around 77 C. But if you take into account the interactions, you get a completely different trend. And in fact, what you see then is that for small amounts of ethanol, you actually see that the vapor pressure increases. In other words, you see a decrease in the boiling temperature with small amounts of ethanol, up to 20% here. And then you see essentially a rapid rise or decrease in the vapor pressure as you approach 100% ethanol. So that's an effect that you would not be able to predict without a model that accounts for these additive effects. And it has an effect when you come to look at the distillation curves. So this is for various ethanol gasoline mixtures. The dotted line here, this is an experiment, is the base gasoline. And here you're seeing different amounts of ethanol going from 5% to 100% ethanol. Looking at the experimental data, if we pick one of them, let's say the 25% ethanol content, you see you reach about 60% by ethanol before you see this rapid rise, and then it follows the gasoline curve. If on the other hand, if we look at the simulation for E20, we just don't see that. We just see a much more gradual rise in the distillation temperature. That's without using this interaction model. But if you use the unifact model, you see something that looks a lot more like the experiment. You see basically at around 60% suddenly an increase in the boiling temperature, consistent with the experimental data. Okay, so we have a multi-component model. We want to use that for realistic fuels, for example, diesel, Jet A, JPA, so on. We can divide those fuels into groups: alkanes, aromatics, cycloalkanes, PAHs, shown by the colors here. And the key thing is, first we want to be able to do is to represent the distillation curve for those different fuels. So here you see for diesel, the black, and the Jet A, JP fuels, the amount of each of these components that would be necessary in order to represent this distillation curve. So that's essentially the approach we're taking in our modeling now, is to come up with a list of surrogates that we think characterize the fuel sufficiently that we can represent the physical properties of the fuel. Of course, we're interested more than just the distillation curve. We're also interested in density, viscosity, surface tension, lower heating value, the amount of saturates in the mixture, the amount of aromatics, olefins, naphthalene, CH ratio, molecular weight. And so for these particular surrogates that you see here, you see comparison between measured and modeled. Most of the results look reasonable. Density, though, turns out to be lower for the surrogates, and that's because the realistic fuels typically have a lot of heavy species higher than C20, for instance, which contributes significantly to the density. So one way to deal with that is just simply to correct the densities to make sure you're using the experimental density, or to add more species. An important thing to realize, though, is that we don't have chemistry for most of these species. Right? So I mentioned to you last time we were talking about chemistry, surrogates, and so on. In order to handle this, what we do is we essentially treat all the alkanes with one chemistry mechanism, all the aromatic components with, say, the toluene mechanism, and cycloalkane to use the naphthalene for that, and for pH. This just shows a little bit more. Here we have a 20-something species representation of diesel fuel published recently. And that allows you to make up for this set of fuels from advanced maintenance activity, so-called face fuels, the amount of paraffins, the amount of propentines, and so on. And we can do that with this list of species that you see here. Very effective. So for instance, for the phase 9 fuel, we have this list of physical surrogate species here. There's pictures of those molecules. Interestingly, here are those activity coefficients that I spoke about, the ones that measure the departure from Rolf's law using the Unifact method. And you can see that for some of these components, there's a significant impact. Essentially, we're changing the vapor pressure by a factor of 2, right, for this particular molecule. Yeah?
So then to go back into engine modeling, would you have to reduce that mechanism?
So we keep all of these species because we're essentially just adding a few more species to the calculation. But then for the chemistry, what we'll do is group them and just say take all of the aromatics and treat them as though they had the properties of toluene in the reaction mechanism. Of course, when you do that, you add all the species of the toluene mechanism, so you're adding lots more species. So this list is relatively short compared to the chemistry. This just shows the distillation profile for phase number 1. A very good agreement with the fields that you see listed. Okay, so that's what I wanted to talk about with regard to the sort of physical models. We discussed vaporization, breakup, collision, coalescence, drag, wall impingement, vaporization. But there's more to it, as I mentioned earlier. When you put this into a CFD code, and remember that all of these things are sub-grid scale models, what you find, disappointingly, is that the results depend on the mesh size. So for example, here, I injected all those classes of drops. I had a 4 millimeter mesh, so each of these mesh cells is pretty wide, actually. And the spray at a given time after the beginning of injection reaches a certain distance. If I now higher the mesh size, I see that my spray penetrates in this rhythm. And finally, I have to get to very fine meshes before I see the spray actually penetrating to a fixed distance. And the reason for this is essentially that on a coarse mesh, the drop drag effects are over-predicted. Essentially, if I have a cell the size of this room and I put throw a droplet in this room, according to the sub-grid scale model, that droplet has to give up its momentum to all of the air in this room, so it slows down rapidly. But if I have a tiny cell, I have to send that droplet into the cell. The air in that cell basically is much less air that has to be accelerated or decelerated. And so I see a different effect depending on the size of the fabrication cell. So this is a big problem, especially in the air injected, where the droplets are, as we indicated before, are not really filling the cell. The other thing is that I mentioned, somebody asked about droplet collision and coalescence. If you have a fine mesh, like this one over here, it's possible you only have 1 or 2 droplets in a cell. And so therefore, there's no collision process that takes place. Compared to the case here, where you have many droplets in the cell, lots of collisions and coalescence. So both of these effects are the explanation behind why this is such good dependent. So to get around that, we have one more empirical model that we've introduced, and it allows us to maintain these coarse mesh sizes, which allows you to do practical calculations. And that is, we assume that when the droplets are injected, that they essentially set the gas in motion as though we had injected a gas jet with the same momentum as the liquid injection. So we can go to gas jet theory and velocities would be. Notice the cell sizes are huge here, but now we're talking about a sub-grid scale effect. So we can essentially, for each droplet in this big cell here, look at what the gas jet theory would predict for the gas velocity in that cell. And instead of using the average velocity for just this trepidation cell, we'll use what the gas jet theory predicts. And when you do that, you only have to do it in those cells very close to the nozzle where you don't have adequate resolution. We find we're able to match the spray penetration adequately over a wide range of mesh sizes. So you can think of this as a sub-grid scale momentum exchange model for large cells via model. Okay, so to validate these models, there's a lot of data out there, but in a way it's kind of disappointing because the interior structure of the spray is not really accessible except through, say, X-ray techniques and so on. So we rely on things like the spray tip penetration as a function of time, measurements that are relatively easy to make, photography, let's say. And then with PDPA, or droplet size instrumentation, we get an idea of the droplet sizes in the spray. This shows multiple gasoline spray, actually SR10 data from these experiments. And they measured droplet sizes at various locations downstream of the nozzle. That's shown over here as a function of time. The measurements of the solid symbols you see here. And here are our predictions using the model I've been describing. A bunch of different cases here. We changed the mesh size from 1 to 3 millimeters. In this case, we kept the time steps the same. You can see that the results are pretty mesh independent. You know, it's not a perfect agreement, but that's not bad. They'll predict soft sizes this class. This is the velocity of the droplets, which also the PDPA instrument is able to provide. You can see fairly good agreement between the solid measured data and the symbols with different mesh resolutions. And then here is the tip penetration as a function of time, so that it's getting penetrated, subtracted typically. And you can see, at least in the range where the measurements are, pretty good agreement. Yeah.
With respect to the previous,
Okay.
I don't know, I want to ask you what to say, but so you have a profile that you apply to, let's say, the mesh that are near the jet. And depending on the position of the droplet, then you obtain a velocity that will influence the particle.
Exactly. So instead of using the CFD calculated gas velocity, we use a gas velocity estimate from gas jet theory.
Doesn't that cause a momentum imbalance?
No, it turns out it's basically what you do to the drop, you have to do to the gas as well. So essentially, the way the curve is formulated, you have a single force that is subtracted from the liquid phase and added to the gas phase. It's the same value. So it has no net effect. Well, let me just, before I say anything else, and pretend you didn't hear this. There's error in the experiment as well. Okay. So we don't really know how bad this is. Making droplet size measurements in a spray is not trivial. Also, these are averages over a cross section here. And there's actually a variation in drop size across this average. So it's actually, there's a lot behind this data that's not really being shown. You know, it would be satisfying to have closer agreement, but basically this is the state of the art.
This is like by far the best match that we have currently.
Mm-hmm. Yeah. Of course, also these measurements are quite far downstream of the nozzle. You know, we have no idea what's happening closer to the nozzle. There is other validation data out there. Just thought I'd mention this. This is work from Sandia. They have a spray bomb that's widely used. And if you go to this website here, much data is available through the engine combustion network, Lyle Pickett's activity. So they have this bomb that can essentially be arranged to have pressures and temperatures similar to those in an engine. And optical access such that you can look at these sprays. One of the things that's of great interest is to try to calculate for vaporizing sprays, how far the liquid penetrates before it's all vaporized. So here you see a simulation, for instance, where the red region here shows the liquid droplets, and by a certain length they've all disappeared. And that's called the liquid penetration length. It obviously depends on temperature. The higher the temperature of the gas in the chamber, the shorter this vaporization, or the faster the vaporization process, the shorter the length. Here you see some comparisons between measured and calculated liquid lengths as a function of the gas density in the environment. And you can see the trends are pretty well respected for, in this case, diesel fuel through a 246 micron hole nozzle. We, again, have looked at the effect of mesh resolution on results like this. Here you see changes in mesh size from 1 to 3 millimeters. In this case, we're keeping the time steps, again, around 1 microsecond. This shows the vapor penetration. In other words, the distance from the nozzle to the tip of the vapor jet. Right? And the other shows the liquid penetration. That's this data down here. And somewhere buried inside all this is the experimental data, but it agrees quite well. The plot on the right shows the effect of time step. During a calculation, the time step is adjusted based on various stability criteria in the numerical scheme. And very few people check time step independence. In fact, you can see we do a reasonable job. There's some problems, though, when we go to very large time steps, especially at early times. But basically, we consider this to be as good as you can do at this time. We also have engine data. This is an optical engine, also at Sandia. It's a Cummins engine with different cases here. I'm not going to go into that at this time. Different mesh resolutions. And here, this just shows the optical layout at the Sandia lab. They have an optical piston. One of the exhaust valves is replaced by a window, so you can look in the combustion chamber. And if you look at the top, or view up through the piston here, you can see those spray plumes. They can measure the liquid length and also the vapor length in an actual engine, an optical engine. And here you see the liquid penetration versus crank angle for one particular operating point. Here we've changed the mesh size from 1 to 3 millimeters, and also the time step over a range from half a microsecond up to 5 microseconds. And you see the simulations predict the liquid length fairly well. Yeah.
What solution scheme is used for the particles?
For which? Position of the particles? Yes, so remember I mentioned we're using the method of characteristics to solve the spray equation. So basically it's just a forward time integration. So the position of the particle dx dt equals v, the particle velocity. It's forward time integration. All right. Okay. So to summarize this part of the presentation, there are pretty well validated spray models now available that capture most of the physics of vaporizing sprays, even under engine conditions. We can deal with realistic fuels with non-ideal vaporization. These spray models basically provide information about how the fuel is distributed in the engine. This is required then for combustion modeling, and if you want to actually use these models to optimize an engine. Spray predictions can be independent of mesh and time step. I should also mention that the overall computer time is a big issue here, so we want to use these coarse meshes as much as we can in order to make these codes useful to industry. And then finally, there's a lot more data available as described, for instance, at the Sandia website. So questions about hour 5? Yeah. All right, let's, yeah.
So regarding the issue, a couple slides, we had the spray model that needed to be grid independent.
Oh, yeah.
So I just was wondering if you changed the, say, the number number of parcels or the number of droplets per parcel as you change the size of the grid, if that would also have that?
Yeah, so I think we mentioned something about that earlier. We have done a lot of sensitivity studies over time where we'll change the number of parcels and number of drops in a parcel and so on. And as long as you have sufficient parcels, the results are independent of the number that you use, because you just need to represent the sort of macroscopic properties, the amount of fuel that's in that computational cell and so on. But you're right. As I get to smaller and smaller cells, eventually I could maybe even use deterministic collision models where I actually follow each of the particles and calculate their trajectories and look at their collision outcomes. But then we're getting away from a model that can be used by an engineer to design an engine. So that's the problem here.
You said that not in the near future will we be able to have predictive spray models, and we also have all these tuning constants within our models that sort of prevent that. So what steps forward should we be looking at to improve the predictive capabilities?
Right.
Not just looking at those tuning constants.
Right. So, for instance, I showed you some results that Mario Trujillo and Marcus Herman and others are doing with DNS simulations of sprays and spray breakup. We're hoping that we can use those kinds of simulations to fix those constants. Because eventually you're going to need to use models like this. I think Mario told me one of his simulations just of the breakup of the jet that I showed you over there was a month on, I think, 256 computers. So that's not going to be helpful if you're designing an engine. But at the end of the day, we can use his results to figure out what drop sizes and what breakup lengths and things like that we can expect, and then tune our models using that data. It's kind of like the reduced mechanism issue with chemistry, right? So, all right, yeah?
You described the penetration when you're looking at spray that's going directly to the engine, probably from the engine to the cylinder head. With new concepts like GDI, where you try to do wall-guided
Sure.
more of a challenge in capturing the spray?
I think I showed you a movie yesterday, but we do those types of simulations as well. The droplets that hit the walls slide along the walls, and they can bounce off the walls. So that's all represented in the models as best we can do. Yeah. Okay, let's move on because I'm running out of time here. So the last part for today. And remember that today really focused on models, right? Spray combustion modeling. Tomorrow, we're going to actually talk more about applications. So depending on your interests, you might find that interesting. But anyway, we're going to talk about heat transfer and emissions modeling in the time we have left today. So heat transfer is very important. About 30% of the fuel energy in a conventional diesel engine is thrown away to wall heat transfer. But aside from that, heat transfer can be very important because it can control the compression ratio in the engine through the avoidance of knock. And essentially, heat transfer influences ignition, and also it can influence engine durability. So here are just some examples of things that can happen. This actually happened in our engine here, where you have cracks appearing between the, in this case, the intake valves, due to high temperature in the chamber here, causing differential expansion in that thin area, leading to major damage in an engine, potentially. Okay, so heat transfer. How does that come about? Well, if we go back to the energy equation, we've discussed all the terms here before, but I added a new term here, which is QR. So we can have radiation heat transfer, especially in a sooty engine where soot radiation is important. So in order to do that, we have to solve essentially the radiation transfer equation. But before we get to discussing that, we also need to worry about the, how we treat the wall heat flux. I mentioned to you before that we had improved the log law of the wall to account for compressibility effects in an engine. And so back here, Alan Hine and I proposed a wall heat transfer or heat flux expression that essentially is a modification of the log law of the world that accounts for the fact that the density is varying due to compressibility effects. Looks very much like the log law of the world, except in the log law of the world, this is not a logarithm, it's a linear difference in temperature. Now, if you include other contributions to the wall heat flux, you get this extra term here. And this term G is essentially the radiative heat flux, or it could be, if you have combustion occurring in the wall boundary layers, you could have a contribution to the wall heat flux as well. But here we're talking about radiation. So G would be the radiation heat flux, or radiative heat flux. So in order to calculate that, we have to solve the radiation transfer equation that's shown over here for the radiation intensity, which is a function of position in the combustion chamber and solid angle. It depends on where the radiation is coming from. And the terms on the right-hand side involve the absorption coefficient, scattering coefficients, extinction coefficient, kappa here, and the black body radiation from surfaces. And then at the end here we have a scattering term. Jim Wiedenhofer in his PhD thesis introduced this model into the code that we run. And basically one of the things that he argued was that the scattering terms can be neglected. So we're really only interested in the absorption coefficient terms when we solve the equations. So this radiation transfer equation is kind of different to equations that you are familiar with, the Navier-Stokes equations and so on, because there's no time-dependent term here. Everything's moving at the speed of light, right? So basically, it's a different type of transfer process than you might have seen before. The radiation intensity at a wall then comes from looking at this equation, and we needed this term in our wall heat flux expression. It involves surface emissivity and the radiative flux reaching the wall. The method that's used to solve this, and many methods used in the literature, but we chose to choose the so-called discrete ordinates method, where basically you divide this solid angle up into a discrete number of angles. The more you choose, the higher the accuracy, but the more work is involved. And so here you see those preferred directions for a case where we had 6 ordinates. So in each cell, basically, you have to store the contributions to the radiation flux that comes from those 6 coordinate directions. And that's what's defined here. M goes from 1 to the number of coordinate directions, the solid angle, and the radiative flux from cell to cell. So that's basically the method that's used to calculate the radiation source terms in the energy equation. You also need the absorption coefficients. So basically, soot is a great absorber. And you also have absorption from gas phase species, notably CO2 and water. But again, we use an expression for the absorption coefficient, which essentially involves a constant times temperature for soot, and then wide band models for CO2, H2O, and those are the main species that are considered. If you take a look at the relative importance of these two terms, what you find is that soot is way more important than the gas phase radiation. In fact, if you do an order of magnitude analysis here, you see that basically you have Stefan Boltzmann constant times T to the 3 for the gas, temperature to the 3 for the gas contribution, and T to the 5 for the soot contribution. So soot is really most important in the radiation models. Okay, so we have now heat flux that is coming from the gas phase. We have both due to temperature gradients in the vicinity of the wall, and then also due to radiative flux to the surfaces. Just a picture showing that you could expect quite a lot of radiative flux from conventional diesel combustion. And what we've done is to basically integrate that with a finite element heat conduction code for the metal components in the engine. So here you have an unstructured mesh for the metal heat conduction problem. And the boundary conditions are such that we get our heat flux from the CFD code. We take into account also oil jet cooling on the undersurface of the piston, for instance. And also we have similar boundary conditions for the head and the liner. And then we essentially have an iterative coupling between these two codes. So we use Kiva. Let's say we start out by assuming constant wall temperatures. We use the heat flux that comes from the Kiva code with the radiation, possibly. We use that then in our heat conduction and components code. This gives us new surface temperatures, which we then feed back to Kiva. We go through an iteration here. And typically, this converges in about 3 or 4 iterations. So it's not a bad process. And at the end of the day, you then have spatially varying surface temperature boundary conditions, which are much more accurate than just assuming, say, a piston temperature or a head temperature. This just shows some results from Jim's thesis work for the Caterpillar engine in our labs, single-cylinder oil test engine. You can see wide variation in piston surface temperature. This red region here corresponds to alignment of one of the jets for a high load operating point, a very high temperature at that piston bowl edge. Similar results for a Cummins engine. Again, temperature scale is kind of hard to see here, but the red are high temperature regions, blue are low temperature regions. So this is very important, especially when we start looking at HCCI type combustion, where the temperature field is so crucial in the engine. This just shows some results of another implication of having radiation and heat loss models in your code. What we're looking at here is the peak piston temperature, so that would be at that edge between the bowl and the squish region, as a function of the time of start of injection for a conventional diesel combustion case with a fairly high load, so equivalence ratio of 0.7. So what you see here is run 1, run 2, run 3. This corresponds to that iteration where we go from Kiva to the HCC code, then back to Kiva. That would be iteration 1, and then do this 3 times. And eventually, you can see we get pretty consistent results. Let's see, run 1 was the square, run 2 was the circle, run 3 was the triangle. Lies in between those first 2. So it seems like it's converging. So the solid lines here are when we do not include radiation in the heat flux calculation. The open symbols, though, are when we do include radiation. And you can see significant impact of radiation on surface temperatures. So we go basically from 600-something degrees, 630 degrees for this case, all the way up to 700 degrees by including radiation in the heat transfer. So basically, we actually saw 34% higher heat loss when we include radiation in the head, 19% the liner, 47% in the piston. So the effect of the radiation actually is interesting because it lowers the gas temperatures. That energy has now been transferred to the wall, so that gas temperature is lower, and that gives you lower NOx. It's seen in this plot here, which shows NOx versus injection timing. The cases with radiation are the circles. So that's this one here. So you see lower NOx compared to the open squares here when you have radiation. And this is done for 2 different loads here, the solid symbols and the open symbol. So basically, we see lower NOx, as much as a 30% reduction in NOx, but higher soot in the simulations that he ran. So if we look at engine emissions, we're talking about NOx and soot here. This is something that is really driving a lot of the research that we've been discussing these last couple of days. In particular, the EPA has set standards on all of these guys you see here, these 6 pollutants: ozone, particulate matter, carbon monoxide, sulfur dioxide, nitrogen oxides, and lead. So lead we don't have to worry about because they took that out of the fuel. Sulfur we don't have to worry too much about because now sulfur is really at low parts per million in diesel fuels, except when you talk about marine fuels, but for truck engines and so on, sulfur is very low. Particulate and nitric oxide are really the key things for the diesel community. Of course, the EPA has a long list of what they call air toxics, mobile source air toxics. There's 21 of those, but there's 6 of them that are particularly noxious: benzene, butadiene, formaldehyde, acetaldehyde, and so on. And, of course, diesel particulate matter. In fact, the National Health Institute just recently announced that, for sure, diesel particulate is a carcinogen, and this has caused the diesel industry a lot of pain recently, because the experiments that they used to make that assessment are actually very old engines. And diesel industry has spent the last 20 years really improving engines, and they don't believe that, that this is a fair assessment. But anyway, bottom line is that emissions are essentially one of the major driving factors for research in engines. So let's look at diesel emissions. Okay, so there's 2 solutions that people have proposed, namely to dilute the combustion process by using a lot of exhaust gas recirculation, lower temperatures, such that you can meet this very low NOx level of around 0.2 grams per kilowatt hour. So some companies, when we're faced with these emissions regulations standards, decided they're no longer going to sell diesel engines. So Caterpillar did that. They said, we're no longer going to sell truck engines because we can't meet these standards. Other companies said, well, we're going to meet them using, in the one case, EGR or selective catalytic reduction, which seems to be the more popular path. Anyway, Navistar went out on a limb and announced that they would not need SCR, and that they were going to use improved engine design, improved air handling, twin series turbochargers, high pressure common rail fuel injection, really hit the problem with a sledgehammer. Other companies like Cummins initially said they were going to use this approach and then switched to SCR. So what is SCR? Here's the engine. We have a diesel particulate filter. That's in all engines basically now to get the soot down to these kind of numbers, very low soot or particulates. And then we have this tank full of another fuel. It's called diesel exhaust fluid, like DEF. It's this molecule here, urea or carbamide. It is sprayed into the exhaust. It decomposes to produce ammonia. And then ammonia is the catalyst agent, which then converts or reduces NOx to nitrogen. So SCR, selective catalytic reduction, as I said, is mentioned and used by now many companies to meet these 2010 emissions levels. Cummins announced this in 2010. They claimed that they actually would get a fuel economy gain by using SCR because they could recalibrate the engine to produce high NOx. So it's important to realize that for a guy driving a truck who spends $100,000 a year on fuel, even a 1% change in fuel efficiency is a meaningful number. So when Cummins said that they would get 3%, 5% fuel economy gain, that was very attractive to them. What they didn't say, though, is that you now need to add this stuff, which they announced would be on the order of 2% of the fuel consumption rate. And there's still some doubt about what this stuff actually costs. In Germany, it's $12 a gallon. Apparently, Cummins says it's around $3 a gallon. So it could be basically you're just replacing diesel fuel with this other fluid. The other thing that's kind of interesting, though, is the cost of this system. For example, Volvo published some data that showed that for a truck, it's about almost $10,000 to add on this SCR system here. And that's because basically you have to change the amount of SCR that's added to the exhaust fluid here Depending on the engine operating condition, you have to worry about the fact that this stuff freezes. It's a mixture of, with water, so it freezes. It also gasifies at high temperature environments. So keeping this dose at the appropriate constant water to urea ratio is very, very complex and requires all sorts of control. The other thing that Volvo has pointed out is that it already cost them $7,000 extra for an engine to meet the 2007 emissions, and that was adding the DPF here, because basically that diesel particulate filter fills up with soot, and you have to burn off that soot occasionally through what's called a regeneration cycle. So you spray fuel into the engine to locally heat up the, or into the exhaust, to heat up the filter to burn off the collected soot. So you add these two numbers together here, and you find that basically engines are now about $15,000, $20,000 more than they were before 2007, which used to be the price of the whole engine. So basically, the engine price has doubled due to the requirement to meet these emissions regulations. It's pretty amazing. This is for heavy-duty engines. Okay, so let's talk now about the kind of models that are used to model, for instance, NOx, and then hopefully we'll have some time to discuss particulate. The standard model is the Zeldovich NOx model, which I'm sure you're all familiar with. Basically, it's the initiation step because you have to break this N2 bond here. And then there's the so-called extended Zeldovich, which includes OH attacking nitrogen atoms to produce NO. What we have done at the Engine Research Center is essentially to create a 12-step NOx model that's based, includes the Zeldovich, but it's based on the Gas Research Institute mechanism. It includes also thermal NOx and prompt NOx, and then some extensions that include interaction with HCN and ammonia. Also, there is some connection between NOx and soot that I'll discuss with you in a minute. So to create that 12-step NOx mechanism, we basically took the GRI mechanism and looked at the species involved and reaction flux diagrams with Senkin. XN plot creates these plots here. And basically, the size of these arrows tells you how important the various paths are going from nitrogen to NO or NO2. And we identified basically these 4 species as being important, N, NO, N2O, and NO2, and 12 reaction steps. They were added then to the ERC-PRF mechanism. This just shows a little bit of a simulation of diesel sprays. So we have an injector up here, and we're just looking at 1/2 of a diesel spray injected into a high temperature environment. So we have combustion occurring. And what I'm showing you here are profiles of NOx using the full GRI mechanism and then using our reduced mechanism for these cases on the right, showing you profiles of NO, NO2, and N2O. So you should compare this with that, this with that, and this with that. And as you can see, the reduced mechanism does a very good job compared to the more detailed mechanism. So here are the 12 steps that are included now along with our PRF mechanism. Other interesting thing that one of my students, Takeshi, explored a little bit was the connection between NOx and soot. From a kinetic standpoint, it was kind of interesting. If you look at low or lean mixtures or even up to stoichiometric mixtures, there's not a very tight connection between the species that are associated with soot production, which we'll be discussing in a minute, such as acetylene, and the species that are involved in NO production. So there's essentially a very loose connection there. But if you go to a very rich mixture, equivalence ratio of 3, for example, here, you find that there's actually a competition for the CH radicals between the soot through the C2H2 path and HCN, which eventually leads to NOx formation. So basically, as you get to richer mixtures, you need to have more of a crosstalk between your soot model and your NOx model. which we thought was kind of interesting. But the requirement then is to really extend your NOx mechanism. So we started out with our simple reduced mechanism from the GRI mechanism with 12 steps for NOx with these 4 species. But now we're going to add additional species and more reactions to account for cases where you are on the rich side of stoichiometric. You can take a look at those numbers and so on at your leisure, but you notice that it involves the CH radical here. There are also, if we want to include other species on the rich side, ammonia and HNCO, another 22 reactions that we found were important. So this is work that Takeshi published, and if you're interested, you can take a look at that. To be honest, in most of the simulations that we do not include this detailed NOx model. We've stuck with the 12-step model. It seems to give reasonable results anyway. So let's finish up by talking about Soot. First thing is, how important is Soot? We already discussed, when we discussed the radiative transfer equation, that radiation is important and that a significant component of the radiation comes from the soot. So Mark Musculus at Sandia did some interesting experiments in his optical engine where he essentially changed the start of injection timing and measured the heat flux, or rather the heat release rate and pressure traces, as you can see here. And then on the next slide, I'll show you the corresponding NOx measurements. But I'm also showing you here Takeshi's simulation results. And you can see we're able to match the data, the colored data are the predictions, and the solid lines here are the experimental data. We were able to match over this wide range of start of injection timings, going from 12 degrees before top dead center all the way to 15 after top dead center. So that was encouraging. We also compared the spatially integrated natural luminosity data obtained from the experiments. And of course, this is arbitrary units, so we can choose a normalization here. But again, these results agreed quite well with Mark's experiments. So we felt like we were doing a reasonable job with both NOx and Soot. And that's kind of shown here. So this is Mark's measured data for those different start of injection timings. As he retarded the injection, the NOx decreased, and then he saw this interesting bump here. And he argued that the reason for this bump is that if you look at the measured Soot data, around this start of injection timing, you suddenly see a big drop in Soot. So that means that the radiation associated with the Soot is no longer important. Now remember I said how the radiation actually lowers the gas temperatures because you're essentially sending that energy to the wall. So a lower gas temperature, you would expect to see a reduction in NOx. And so his argument was that if you don't have radiation, you're going to see an increase in NOx. And that explains this bump. So this shows our simulation results where we include radiation or do not include radiation in the blue without radiation, red with radiation. And you can see kind of a hint of what he saw in his experiment here. But basically, we were not able to quantitatively get the agreement that he saw. But it was enough that we felt that the models were doing a reasonable job. Basically, the radiation lowered the predicted NOx, if we looked at the NOx here, by about 7%. If we just removed the soot particles, we saw that that lowered the predicted NOx as well by about 2.5%. Overall, though, our NOx model underpredicted the measured NOx slightly. And this is actually kind of a fundamental problem because, remember, the NOx prediction is very strongly dependent on the temperature. The temperature is very strongly dependent on the fuel-air mixing. And if you have, for example, different estimates of how the fuel-air mix through your spray model or through your turbulence model, we found, for instance, NOx predictions are very sensitive to your assumption of the Schmidt number in your mass transfer. So basically, we're dealing with a complicated physical process here, And you have to kind of accept the fact that there are going to be discrepancies between experiment and model. Okay, so this just finally shows Takeshi's comparison with those detailed NOx models with the 12-step model all the way up to the GRI with 235 steps. The experimental data is this data down here. And you can see all the models give roughly the right trend. This is NOx versus load or IMEP. The model that does the best actually is the GRI MEC model, this triangles here. But ultimately, all the trends are captured even with the simpler 12-step model, especially if you allow for the fact that there is going to be some discrepancy between calculated NOx and experiment. Yeah?
What reactions is that sensitive to? Why?
It's ultimately temperature.
Just the temperature?
Yeah. So, if you don't predict the temperature correctly, you don't get the NOx. It's as simple as that. Okay, so to finish up, let's talk about Soot models. Long history of models that we've looked at the Engine Research Center, starting with the simpler two-step models, so-called Hirayasu models, looking at multi-step phenomenological models, and more recently, trying to include more PAH chemistry in our Soot models. If you're interested in reading up about Soot, there's some great references that are listed down here that describe Soot processes in engines and in more general applications. So the simple Hirayasu two-step model basically says that the net Soot mass, the rate of change of mass in, say, a computational cell, is determined by the difference between the rate with which I form Soot and the rate with which Soot is oxidized. I have an Arrhenius expression for the Soot formation rate, and I use the Nagel-Strickland-Constable model. We'll talk more about this a little bit later for calculating the oxidation rate. In the original Hirayasu model, he assumed that the Soot formation was proportional to the mass of fuel in the computational cell. That's great, but when you couple that with a detailed chemistry model, what is the fuel? So basically, we bypassed his approach, and we use instead the acetylene concentration to drive the Soot model in the simple two-step model. So acetylene is taken as the Soot precursor. Here are some of the other parameters in the model. You can see details in these references. Of course, once again, we have to tune these models. This quantity here, ASF, is a tuning constant that we found with the use of these models has to vary quite widely from engine to engine. And so that really was one of the motivations for trying to improve these models. The next step was to assess the performance of the Soot models against experimental data. So we have some data from Lyle Pickett and Dennis Siebers at Sandia where they have this constant volume vessel. They measure liftoff length. I forget which fuel this was here. Probably it was N-heptane. Liftoff length as a function of the temperature of the gas in the chamber, which essentially establishes the location of the flame. And then downstream of that, they use LII, laser-induced incandescence, to measure the amount of soot as a function of position, and also for these different images for different temperatures in the chamber. And what they find is that the soot mass, here micrograms as total soot mass as a function of distance from the injector, this black line, looks like this. You form the soot, and then you oxidize the soot. When we use the two-step model, we get this result shown in the red there. And basically, the model essentially says the moment you get some acetylene, you start forming soot. And that occurs right at the formation, the liftoff length location. And so there's a qualitative disagreement, even if you tune the soot model to get roughly the same magnitude. So this is emphasized in this schematic picture that Lyle and others have produced, where essentially you're looking at diesel injection, or in this case, in heptane. You see that the fuel breaks down to produce formaldehydes. Then one has ignition, or second stage ignition, the formation of a diffusion flame. So we're moving away from the injector here. Then there's regions where PAHs appear, and then eventually soot. So this whole process is not represented when you use the simple two-step model. In fact, here we see our simulations. We get nice agreement with the location of the formaldehyde, reasonable agreement with the location of the flame, but we get the soot occurring right from the beginning. So how do we deal with this? Well, if you go back and take a look at the data, this is from Dale Tree's paper, for instance, you essentially have these processes. You have the chemistry that leads to the formation of the soot precursor species. We've already discussed this chemistry when we spoke about combustion. Those soot precursor species include acetylene, C2H2, propagyl. These combine to form the first aromatic components. And then they essentially progressively grow through to polyaromatic species. And then you have basically processes that lead to the soot particle inception, particle coagulation, soot surface growth, and then, of course, the competing soot oxidation. So all of these processes need to be somehow in your soot model, and they were not in our two-step model. So one approach is to try to include in our chemistry a representation for the PAH species. We found in the literature a reduced PAH mechanism that essentially came from Wang and Franklock. It's basically 20 species, 52 reactions. So we added that to our baseline multichem mechanism that I presented yesterday. So this mechanism essentially allows you to track, starting with acetylene and propagyl, the formation all the way up to the A4, the pyrene polyaromatic hydrocarbon. This just shows some of the important reactions in that mechanism, 20 species and 52 reactions. Here's a simulation of one of those experiments of Lyle at Sandia. Here's the experimental data. Here he's showing the soot volume fraction as a function of distance from the injector. Here, once again, is the flame liftoff length. Looks similar to the data I showed you before. And now you see the CFD simulation. And what I'm showing you here is essentially the, I think this was, OK, this is soot mass fraction. Yeah. Qualitatively, the soot is now in the right location. This plot here shows the amount of carbon that's tied up in those precursor species. Here's the acetylene. Here's the experimental soot mass. So you see similar amounts of carbon in the acetylene and in the soot mass. But if you look at the precursor species, A1, A2, A3, A4, you see that is really a very small amount of carbon tied up in these species. They essentially exist and then go straight through to soot in the model. So this describes how we implement the soot model in our CFD code. Basically, we start out with soot inception, where we start from the pyrene, the A4, and with a certain rate taken from the literature, we produce the first soot or carbon particles or graphitization. Then we have acetylene-assisted surface growth, essentially acetylene combining with whatever carbon you've created here as your soot contribution. This depends on the surface area of the soot, so we have to track the surface area. For that, we need to know the soot diameter. So to calculate the soot diameter, we actually have to solve partial differential equations for the mass fraction of soot and for the number density, the number of soot particles. And I'm going to show you these partial differential equations in a minute. But basically, with those known, the soot mass fraction and the number of particles, we can calculate the diameter, therefore the surface area, and therefore we can calculate the rate of surface growth, because that depends on the square root of the surface area. We also have to account for soot coagulation. We have data from Liang that we use for that model. We'll have the O2-assisted surface oxidation, or soot oxidation. This is the NSC model that I spoke of before, the Nagel-Strickman-Constable model. Here are the rate coefficients. Again, this is a model that's widely used in the literature, which tracks basically the dependence of oxygen for soot oxidation on the partial pressure of the oxygen and through all these rate constants that you see here. There's also the Fenimore-Jones OH assisted oxidation. We include that also in our soot model. And then finally, PAH assisted surface growth. So instead of just relying on the acetylene to grow the soot particles, we can also include the PAH. This turns out to be a relatively small contribution because I told you the PAHs are actually there in relatively small amounts. Okay, I mentioned those partial differential equations. So here is the transport equation. M here can either be the soot species density or the soot number density. So it's one of those two. So this is two partial differential equations. We can calculate then the rate of change, say, of soot species density due to convection, diffusion, thermophoretic effects, and also source terms. So these, in this system here, the number density is treated as a passive species, and the source terms are shown over here. Again, this comes from the literature, but basically knowing the soot mass fraction and the number density, we can get the soot particle size, which then gives us the surface area. So here, this shows some results. We had actually two different PAH mechanisms, a more reduced one and a more detailed one. This is published in Gokul Vishwanathan's thesis and also in Combustion Science and Technology. You can see that not only are we able to predict pretty much the right location of the soot in those simpler experiments, but also the total soot mass. So this is experimental data from Lyle, these solid squares you see here, and the symbols here show the predictions using, in this case, PAH1, the simpler model. And this is another case down here. We can also get fairly good agreement with the measured data. The other interesting thing that the model gives you is shown in the plot on the right. This shows how much of the soot mass has a certain diameter. So each of these histograms corresponds to a certain diameter particle. And what we're changing here is the injection pressure. So the white open histograms are the highest injection pressure, 190 megapascal injection, whereas the gray ones on the right here are low injection pressure, 40 megapascal. And as you can see, the model actually predicts, which is seen experimentally, that the soot particle size changes with injection pressure. And in particular, high injection pressures lead to smaller effective soot particle size. We've also done some simulations with the soot model of the Sandia optical engine. Again, this is in Mark Musculus's lab, where he has made extensive measurements of soot using LII and other techniques. Some description of the engine here. It's a heavy-duty Cummins single-cylinder optical engine. He's operated this engine over a wide variety of operating conditions, including high-temperature combustion with diffusion combustion or premixed combustion, and then also low-temperature combustion with early injections or late injections. Some of my students have spent time with Mark doing some of these experiments. We've made comparisons, for example, of OH distributions in the engine, soot distributions in the engine seen in the experiments, again with simulation results. So Caroline spent a lot of time working with Mark and produced some of these results here. Very good agreement between predicted results for soot location, OH, and so on. So we were very happy with those agreements. In particular, the red here shows the soot location, and you can see that we're picking that up with our coarse mesh models using the gas jet and also with fine mesh resolution without the gas jet model. This shows cylinder pressure versus crank angle for high temperature combustion and low temperature combustion. We can match those reasonably well. But most importantly is this plot on the right here, where you see significantly different amount of in-cylinder soot. This is total soot in the chamber as a function of crank angle for these various different combustion regimes. So the black data here corresponds to more or less conventional diesel combustion, high temperature combustion with diffusion flame combustion. You see it predicts way more, or the experimental shows way more soot than for these low temperature combustion regimes. And the model, the dashed lines here, is able to pick up that trend when you compare, for example, the black against some of these other cases down here. We do have discrepancies, like, for example, for the high temperature combustion, long ignition delay, the experiment is this red here, the model is this red. So there's still work to be done in terms of improving these soot models. But these predictions are way better than we were able to get with the two-step model. So we've really seen a significant improvement. All right, so where do we go from here? I spoke today at length about multi-component fuel vaporization models. There has been really very little attempt to couple the details of the multi-component fuel description with soot modeling. Essentially, all we do is we take the acetylene that's produced at the end of the day and use that to drive the soot models. But this doesn't really allow you to consider, for instance, you might have aromatic components in the fuel that go more directly to soot. So that's an area that we're currently trying to improve right now. We have some experimental data where we're using a PRF fuel mixed with toluene and comparing the soot that's produced with different levels of toluene with what the models predict to see just how important this path would be. The other thing that we've noticed recently, and on Friday, tomorrow, I'll be talking about some of the combustion work that we're doing currently with low temperature combustion, is that when you collect the soot on a filter, you see completely different looking soot depending on the combustion regime. So for conventional diesel combustion, you get this black stuff that you see coming out of the exhaust of a truck in front of you on the highway. When you go to PCCI, this is early injection, premixed charge compression ignition, it turns kind of brown. And when you use dual fuel reactivity controlled compression ignition, which I'm going to tell you about more tomorrow, basically you get what essentially just turns the paper a tan color. We have done some, we're collaborating with people at Pacific Northwest Labs, and they have taken some of our soot samples and examined them with TEM. And basically, they find the soot looks very different when you compare it for these different operating conditions. And in particular, for RCCI, you can't really call it soot anymore. You have to call it particulate matter because it's basically 99% fuel that is condensed onto very few elemental carbon particles. So if you look at the TEMs here, most of this is high molecular weight hydrocarbons. It's not really carbon anymore. So we have to rethink our soot models to be able to predict that. And that's something that's currently in progress. That's all I wanted to talk about today. So happy to take any questions.
So I think a little bit earlier you had that, it's the HCC code, the heat conduction, and it almost looks like you're starting to get towards having like a finite element model for the engine bar, the piston block. Is that something that's kind of the next step to be able to measure like the stresses?
Sure, yeah. In fact, you can use that same mesh to look at differential expansion in the engine, and in the auto companies, they already do that. The new thing here is coupling it with the CFD for the combustion. Yeah. Yep.
How important do you think cycloalkenes are in performance of surrogates, especially for gasoline?
So certain parts of the distillation curve really rely on having some of those, the naphthenes, that are in intermediate temperature range. So you need something to represent that. Otherwise, you don't get the distillation curve accurately. So that's from the physical standpoint. But for chemistry, they typically have intermediate ignition delays. So it could be that they're important also, depending on what you're looking at. For gasoline, if you're talking about spark ignition, maybe it's not so important. But if you're talking about knock, then you have to worry about ignition processes, and there it might be important. We'll talk about knock and so on also tomorrow.